Today is going to be one of the more difficult lectures of the term, so put on your thinking caps, as they say in elementary school. The topic is going to be what's called the convolution. The convolution is something very peculiar that you do to two functions to get a third function. It has its own special symbol, f of t. Asterisk is the universal symbol that's used for that. So this is a new function of t which bears very little resemblance to the ones f of t that you started with. I'm going to give you the formula for it, but there are two ways of motivating it, and both are important. There's a formal motivation, which is why it's tucked into this section on Laplace transform. And the formal motivation is the following. Suppose we start with a Laplace transform of those two functions. Now, the most natural question to ask is, since Laplace transforms are really a pain to calculate, is from old Laplace transforms, is it easy to get new ones? And the first thing, of course, summing functions is easy. That gives you the sum of the transforms. But a more natural question would be, suppose I want to multiply f of t and g of t. Is there hopefully, some neat formula? If I multiply the product of take the product of these two, is there some neat formula for the Laplace transform of that product? That would simplify life greatly. And the answer is there is no such formula, and there never will be. Well, we will not give up entirely. Suppose we ask the other question. Suppose instead I multiply the Laplace transforms. Could that be related to something I cook up out of f of t and g of t? Could it be the transform of something I cook up out of f of t and g of t? And that's what the convolution is for. The answer is that f of s times g of s turns out to be the Laplace transform of the convolution. The convolution, and that's one way of defining it, is the thing that the function of t that you should put in there in order that its Laplace transform turn out to be the product of f of s times g of s. Now, I'll give you in a moment the formula for it, but I think I'll give you 1¼ minutes of, well, 2 minutes of motivation as to why there should be such a formula. Now, I won't calculate this out to the end because I don't have time, but here's the reason why there should be such a formula, and you might suspect, and therefore it will be worth looking for. It's because, remember I told you where the Laplace transform came from, that the Laplace transform was the continuous analog of a power series. So that when you ask a general question like that, the place to look for is if you know an analogous idea, say, does it work, something like that work there? So here I have a power series, summation an x to the n. Remember, you can write this in computer notation as a of n to make it look like f of n, f of t. And the analog is between n is turned into t when you turn a power series into the Laplace transform, and x gets turned into e to the negative s, and one formula just turns into the other. Okay, so there's a formula for f of x. This is the analog of the Laplace transform. And similarly, g of x here is summation bn x to the n. Now, again, the naive question would be, well, suppose I multiply the two corresponding coefficients together and add up that power series, summation an bn times x to the n. Is that somehow, or it's some related to f and g? And of course, everybody knows the answer to that is no. Has no relation whatever. But suppose instead I multiply these two guys. Well, in that case, I'll get a new power series. I don't know what its coefficients are, but let's write them down. Let's just call them CNs. So what I'm asking is, if this corresponds to the product of the two Laplace transforms, and what I want to know is, is there a formula which says that Cn is equal to something that can be calculated out of the AI and the Bj? Now, the answer to that is yes, there is. And the formula for Cn is called the convolution. Now, you could figure out this formula yourself. You figure it out. Anyone who's smart enough to be interested in the question in the first place is smart enough to figure out what that formula is. And it will give you great pleasure to see that it's just like the formula for the convolution that I'm going to give you now. So what is that formula for the convolution? Okay, hang on. Now, you're not going to like it. But you didn't like the formula for the Laplace transform either. You felt wiser, grown up getting it, but it's a mouthful to swallow. It's something you get used to slowly, and you'll get used to the convolution equally slowly. So what is the convolution of f of t and g of t? It's a function calculated according to the corresponding formula. It's a function of t. It's the integral from 0 to t of f of u. U is a dummy variable because it's going to be integrated out when I do the integration. G of t minus u dt. That's it. I didn't make it up. I'm just bearing the bad news. Well, what do you do when you see a formula that seems to, well, the first thing to do, of course, is try calculating, just to get some feeling for what kind of a thing, what's this going to, let's try some examples. Let's see, let's calculate, what would be a modest beginning? Let's calculate the convolution of t with itself. Or better yet, let's calculate the convolution just so that you can tell the difference. T with t squared. T squared with t, make it a little easier. By the way, the convolution is symmetric. F star g is the same thing as g star f. Let's put that down explicitly. I forgot to last period. So tell all the guys who came to the 1 o'clock lecture that you know something that they don't. Now, that's a theorem. It's commutative. This operation is commutative, in other words. Now, that has to be a theorem because the formula is not symmetric. The formula does not treat f and g equally. And therefore, this is not obvious. It's at least not obvious if you look at it that way, but it is obvious if you look at it that way. Why? In other words, f star g is the guy whose Laplace transform is f of s times g of s. Well, what would g star f be? That would be the guy whose Laplace transform is g times f. But capital F times capital G is the same as capital G times capital F. So it's because the Laplace transforms are commutative, ordinary multiplication is commutative, it follows that this has to be commutative too. So I'll write that down. Since F times G is equal to GF. And you have to understand that here I mean these are the Laplace transforms of those guys. But it's not obvious from the formula. Okay, let's calculate the Laplace transform of, the convolution of t star. Let's do it by the formula. All right, by the formula, I calculate integral 0 to t. Now, I take the first function, but I change its variable to the dummy variable u. So that's u squared. I take the second function and replace its variable by u minus t. So this is times t minus u, sorry. Okay? Do you see that this, to calculate that, this is what I have to write down? That's what the formula becomes. Any question? Is it anything wrong? Oh, sorry, the du. The integration is with respect to u, of course. This should be u. Thanks very much. Okay, let's do it. So it is. Integral of u squared t is, remember, it's integrated with respect to u, so it's u cubed over 3 times t. The rest of it is the integral of u cubed, which is u to the 4th over 4. All this is to be evaluated between 0 and t. At the upper limit, so I put u equal t, I get t to the 4th over 3 minus t to the 4th over 4. Of course, at the lower limit, u is 0, so both of these are terms of 0. There's nothing there. And the answer is, therefore, t to the 4th divided by a third minus a quarter is a 12th. So that's doing it from the formula. But, of course, there's an easier way to do it. We can cheat and use the Laplace transform instead. If I Laplace transform it, the Laplace transform of t squared is what? Is 2 factorial divided by s cubed. The Laplace transform of t is 1 divided by s squared. And so, because this is the convolution of these, it should correspond to the product of the Laplace transforms, which is 2 over s to the 5th power. Well, is that the same as this? What's the Laplace transform of? In other words, what's the inverse Laplace transform of 2 over s to the 5th? Well, the inverse Laplace transform of 4 factorial over s to the 5th is how much? That's t to the 4th, right? Now, how does this differ? Well, to turn that into that, I should divide by 4 times 3. So this should be 1/12 t to the 4th. 1 over 4 times 3, because this is 24 and that's 2. So divide by 12 to turn one constant into the other. So it works, at least in that case. But now notice, this is not an ordinary product. The convolution of t squared and t is not something like t cubed, it's something like t to the 4th power, and there's a funny constant in there too. Very unpredictable. Let's look at the convolution. Let's take another example of the convolution. Let's do something really humble, just to show you that this, even at the simplest example, this is not trivial. Let's take the convolution of f of t with 1. Can you take, 1 is a function just like any function, but you get something out of the convolution? Yes, yes. Let's just write down the formula. Now, I can't use the Laplace transform here because you won't know what to do with it. You don't have that formula yet. It's a secret one that only I know. So let's do it. Let's calculate it out the way we're supposed to. So it's the integral from 0 to t of f of u. And now what do I do with that 1? I'm supposed to take, the 1 is the function g of t, and wherever I see a t, I'm supposed to plug in t minus u. Well, I don't see any t there. But that's something for rejoicing. There's nothing to do to make the substitution. It's just 1. So the answer is, this curious thing, the convolution of a function with 1, you integrate it from 0 to t. Well, as they said in Alice in Wonderland, things are getting curiouser and curiouser. I mean, what is going on with this crazy function, and where are we supposed to start with it? Well, I'm going to prove this for you, mostly because the proof is easy. In other words, I'm going to prove that that's true. And as I give the proof, you'll see where the convolution is coming from. That's number 1. And number 2, the real reason I'm giving you the proof, because it's a marvelous exercise in changing the variables in a double integral. Now, that's something you all know how to do, even the ones who are taking 1802 concurrently, and I didn't advise you to do that. But I've arranged the course so it's possible to do. But I knew that by the time we got to this, you would already know how to change variables in a double integral. So, and in fact, you'll have the advantage of remembering how to do it because you just had it a week or two ago, whereas all the other guys, it's something dim in their distance. And so I'm reviewing how to change variables in a double integral. I'm showing you it's good for something. So what we're out to try to prove is this formula. Let's put that down and so you understand. Okay, let's do it. Now, we'll use the desert island method. So you have as much time as you want. You're a desert island. In fact, I'm going to even go it the opposite way. I'm going to start with, you got a lot of time on your hands, say, gee, I wonder if there's if I take the product of the Laplace transforms, I wonder if there's some crazy function I could put in there which would make things work. You've never heard of the convolution. You're going to discover it all by yourself. Okay, so how do you begin? So we'll start with the left-hand side. We're looking for some nice way of calculating that as the Laplace transform of a single function. So the way to begin is by writing out the definitions. We couldn't use anything else since we don't have anything else to use. Now, looking ahead, I'm going to not use t. I'm going to use two neutral variables when I calculate. After all, the t is just a dummy variable anyway. You'll see in a minute the wisdom of doing this. So it's this times the integral, which gives the Laplace transform of g. So that's e to the negative sv, let's say, times g of v dv. Okay, everybody can get that far. And now we have to start looking. Well, this is a single integral, an 1801 integral involving u, and this is an 1801 integral involving v. But when you take the product of two integrals like that, remember, when you evaluate a double integral, there's an easy case where you don't, it's much easier than any other case. If you could write the inside, if you're integrating over a rectangle, for example, and you can write the integral as a product of a function just of u and a product of a function just as v, then the integral is very easy to evaluate. You can forget all the rules. You just take all the u part out, all the v part out, and integrate them separately, a to b, c to d. That's the easy case of evaluating a double integral. It's what everybody tries to do, even when it's not appropriate. Now, here it is appropriate, except I'm going to use it backwards. This is the result of having done that. If this is the result of having done it, what was the step just before it? Well, I must have been trying to evaluate a double integral as u runs from 0 to infinity and v runs from 0 to infinity of what? Well, of the product of these two functions. Now, what is that? E to the minus su times e to the minus sv. Well, I must surely want to combine those. E to the minus su times e to the minus sv. And what's left? Well, what gets dragged along? Du dv. This is the same as that because of that law I just gave you. This is the product of a function just of u and a function just of v. And therefore, it's okay to separate the two integrals out that way. Because I'm integrating over sort of a rectangle. It goes to infinity that way and infinity that way. But what I'm integrating is over the plane, in other words, this region of the plane. As u, v goes from 0 to infinity, 0 to infinity. Now, let's take a look. What are we looking for? Well, we're looking for, we would be very happy if u plus v were t. Let's make it t. In other words, I'm introducing a new variable, t, u plus v, and it's suggested by the form in which I'm looking for the answer. Now, of course, you then have to, we need another variable. We could keep either u or v. Oh, let's keep u. That means v, this game of musical chairs, v got dropped out. Well, we can't have three variables. We only have room for two. But we will remember it. Rest in peace, v was equal to t minus u in case we ever need him again. Okay, let's now put in the limits. Let's put in the integral, the rest of the change of variable. So it's e. So I'm now changing it to these new variables, t and u. So it's e to the negative st. Well, f of u I don't have to do anything to. But g of v, I'm not allowed to keep v. So v has to be changed to t minus u. Amazing things are happening. Du. Now I want to change this to an integral du dt. Now for that you have to be a little careful. We have two things to do to figure out this, what goes with that, and we have to put in the limits also. Now those are the two non-trivial operations when you change integrals change variables in a double integral. So let's be really careful. Let's do the easier of the two first. I want to change from du dv to du dt. And now to do that, you have to put in the Jacobian matrix, the Jacobian determinant. Aha! How many of you forgot that? I won't even bother asking. Oh, come on, you only lose 2 points. It doesn't matter if you put in the Jacobian. As you see, you're going to forget something, you'll lose less credit for forgetting that than anything else. So it's the Jacobian of u and v with respect to u and t. So to calculate that, you write u equals u, v equals t minus u. And then the Jacobian is, blah, 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 blah. The matrix of the determinant of partial derivatives. So it's the determinant whose entries are the partial of u with respect to u, the partial of u with respect to t, but these are independent variables, so that's 0. The partial of v with respect to u is -1. The partial of v with respect to t is 1. So the Jacobian is 1. So if you forgot it, no harm. So the Jacobian is 1. Now, more serious, and in some ways, I think for most of you, the most difficult part of the operation is putting in the new limits. Now, for that, you look at the region over which you're integrating. I think I better do that carefully. I need a bigger picture. That's really what I'm trying to say. So here is the UV coordinates, and I want to change these to UV to UT coordinates. The integration is over the first quadrant. So what you do is, when you do the integral, the first step is u is varying and t is held fixed. So in the first integration, u varies, t is held fixed. Now, what does holding t fixed in this picture mean? Well, t is equal to u plus v, so u plus v is fixed. Is a constant, in other words. Now, where are the curves along which u plus v is a constant? Well, they are these lines. These are the lines along which u plus v equals a constant, or t is a constant. The reason I'm holding t a constant is because the first integration only allows u to change. T is held fixed. Okay, you let u increase. As u increase and t is held fixed, I'm traversing these lines in this direction. That's the direction on which u is increasing. I integrate from the point, from the u value where they leave the region, enter the region. What's the u value where they enter the region? U is equal to 0. Everybody would know that. Not so many people would be able to figure out what to put for where it leaves the region. What's u, the value of u, when it leaves the region? Well, this is the curve v equals 0, but v equals 0 is, in another language, u equals t. T minus u equals 0, or u equals t. In other words, they enter the region where u equals 0, and they leave where u is t, has the value t. And how about the other guys? For which t's do I want to do this? Well, I want to do it for all these t values. Well, now the t value here, that's the starting one. Here, t is 0, and here t is not 0. And if I go out and cover the whole first quadrant, I'll be letting t increase to infinity. The sum of u and v I will be letting increase to infinity. So it's 0 to infinity. So all this is an exercise in taking this double integral in uv coordinates and changing it to this double integral, an equivalent double integral over the same region, but now in ut coordinates. And now that's the answer. Somewhere here is the answer. Because look, if I... since the first integration is with respect to u, this guy can migrate outside because it doesn't involve u. That only involves t, and t is only caught by the second integration. So I can put this outside, and what do I end up with? The integral from 0 to infinity of e to the negative st times, what's left? A funny expression, but you're on your desert island and found it. This funny expression, integral from 0 to t, f of u, g of t minus u, du. In short, the convolution. Exactly the convolution. So all you have to do is get the idea that there might be a formula, sit down, change variables, the double integral, and echo, you got your formula. Well, I would like to spend much of the rest of the period. In other words, so that's how it relates to the Laplace transform. That's how it comes out of the Laplace transform. Here's how to use it, calculate it either with the Laplace transform or directly from the integral. And of course, you'll solve problems, Laplace transform problems, differential equations using the convolution. But I have to tell you that most people, convolution is very important, and most people who use it don't use it in connection with the Laplace transform. They use it for its own sake. The first place I learned that, outside of MIT people use the convolution was actually from my daughter who, she's an environmental engineer, a consultant, environmental consultant. She does risk assessment, stuff like that. But anyway, she had this paper on acid rain she was trying to read for a client. And she said, it was something about calculating acid rain falls on soil, and then from there the stuff leaches into a river, but things happen to it on the way. The soil combines with it in various ways, reduces the acidity, and things happen. Chemical reactions take place, blah, 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 blah. Anyway, she said, well, then they calculated at the end how much the river gets polluted, but she said, but it's a convolution. She said, well, what's a convolution? So I told her she was too young to learn about the convolution, and so I thought I'd better look it up first. I of course knew what the convolution was, but I was a little puzzled at that application of it. So I read the paper; it was interesting, and in thinking about it, then other people have come to me. Some guy with a problem about they had drilled ice cores in the North Pole, and from the radioactive carbon and so on, with deducing various things about the climate, 60 billion years ago. And it was all convolution. He asked me if I could explain that to him. So let me give you a sort of an all-purpose thing, a simple all-purpose model which can be adapted, which is a very good way of thinking of the convolution, in my opinion. It's a problem of radioactive dumping. It's in the notes, by the way, so I'm just, if you want to take a chance and just listen to what I'm saying rather than scribbling everything down, maybe you'll be able to figure it out from the notes also. So the problem is, we have some factory or a nuclear plant or something like that. It's producing nuclear material, radioactive waste, not always at the same rate, and then it carts it and dumps it on a pile somewhere. So radioactive waste is dumped, and there's a dumping function. I'll call that f of t, the dump rate. That's the dumping rate. Let's say T is in years. You like to have units. And quantity, kilograms, I don't know, whatever you want. Now, what does the dumping rate mean? The dumping rate means that if I, on the time axis, if I have two times which are close together, for example, 2 successive days, new midnight on 2 successive days, then there's a time interval between them. I'll call that delta t. To say the dumping rate is f of t means that the amount dumped in this time interval, in the time interval from ti to ti plus 1, is approximately, not exactly, because the dumping rate isn't even constant within this time interval, but it's approximately the dumping rate times the time over which the dumping was taking place. That's what I mean by the dump rate. And it gets more and more accurate the smaller the time interval you take. Okay, now here's my problem. The problem is you start dumping at time t equals 0. At time t equal t, how much radioactive waste is in the pile? Now, what makes that problem slightly complicated is radioactive waste decays. If I put some at certain day and then go back several months later, and nothing's happened in between, I don't have the same amount that I dumped because a fraction of it decayed. I have less. And our answer to the problem must take account of, for each piece of waste, how long it has been in the pile, because that takes account of how long it had to decay and what it ends up as. So the calculation, the essential part of the calculation will be that if you have an initial amount of this substance and it decays for a time t, this is the amount left at time t. You know, this is the law of radioactive decay. You knew that coming into 1803. Although it's, of course, a simple differential equation which produces it, but I'll assume you simply know the answer. K depends on the material, so I'm going to assume that the nuclear plant dumps the same radioactive substance each time. It's only one substance I'm calculating, and K is it. So assume the K is fixed. I don't have to change from one K from one material to a K for another because it's mixing up the stuff. Just one material. Okay, and now let's calculate it. Here's the idea. I'll take the t-axis, but now I'm going to change its name to the u-axis. You'll see why in just a second. Starts at 0. I'm interested in what's happening at the time t. How much is left at time t? So I'm going to divide up the interval from 0 to t on this time axis into, well, here's u0, the starting point, u1, u2. Let's make this u1. Oh, curses. u1, u2, u3, and so on. Let's call this un. Or maybe un plus 1. Well, it doesn't matter. Okay. Now, the amount so what I'm going to do is look at the amount, take a time interval from ui to ui plus 1. This is a time interval delta u. Divided up into equal time intervals. So the amount dumped in the time interval from ui to ui plus 1 is equal to approximately f of ui, the dumping function there, times delta u. We calculated that before. That's what the meaning of the dumping rate. By time t, how much has it decayed to? It has decayed. How much is left, in other words? Well, this is the starting amount. So the answer is going to be, it's f of ui times delta u times this factor, which tells how much it decayed. Now, so times. So this is the starting amount at time ui. That's what it was first dumped. And this is the amount that was dumped. Times, multiply that by e to the minus k times. Now, what should I put up in there? I have to put the length of time that it had to decay. What is the length of time that it had to decay? It was dumped at ui. I'm looking at time t. It decayed for the time length t minus ui. The length of time it had on the pile. So the stuff that was dumped in this time interval, at time t, when I come to look at it, this is how much of it is left. And now all I have to do is add up that quantity for this time, the stuff that was dumped in this time interval, plus the stuff dumped then, plus and so on, all the way up to the stuff that was dumped yesterday. And the answer will be, therefore, the answer will be the total amount left at time t that is not yet decayed will be approximately, you add up the amount coming from the first time interval plus the amount coming in, so on. So it will be f of ui, I'll save the delta u for the end, times e to the minus k times t minus ui times delta u. So these two parts represent the amount dumped, and this is the decay factor. And I add those up as I runs from, well, where did I start? From 1 to n, let's say. And now let delta t go to 0. In other words, make this more delta u go to 0. Make this more accurate by taking finer and finer subdivision. In other words, instead of looking every month to see how much was dumped, let's look every week, every day, and so on, to make this calculation more accurate. And the answer is, this approaches the exact amount, which will be the integral. This sum is a Riemann sum. It approaches the integral from 0 to, well, I'm adding it up from u1 equals 0 to un equals t, the final value. So it will be the integral from the starting point to the ending point of f of u e to the minus k times t minus u du. That's the answer to the problem. It's given by this rather funny-looking integral, but from this point of view, it's entirely natural. It's a combination of the dumping function. This doesn't care what the material was. It only wants to know how much was put on every day. And this part, which doesn't care how much was put on each day, it just is an intrinsic constant of the material involving its decay rate. And this total thing represents the total amount, and that is, what is it? It's the convolution of f of t with what function? E to the minus kt. It's the convolution of the dumping function and the decay function. And the convolution is exactly the operation that you have to do that. Okay, so I think this is the most intuitive approach, physical approach to the meaning of the convolution. In this particular, you say, well, but that's very special. Okay, so it tells me what the meaning of a convolution with an exponential is, but what about the convolution with all the other functions we're going to have to use in this course? They can all be interpreted just by being a little flexible in your approach. I'll give you two examples of this. Well, three. First of all, I use it for, in the problem set, I ask you about a bank account. That's not something any of you are interested in. Okay, so how about, suppose instead I dump garbage. Undecaying. So something that doesn't decay at all. What's the answer going to be? Well, the calculation will be exactly the same. It'll be the convolution of the dumping function. The only difference is that now the garbage isn't going to decay, so no matter how long it's left, the same amount is going to be left at the end. In other words, I don't want an exponential decay function. I want the function 1, the constant function 1, because once I stick it on the pile, nothing happens to it. It just stays there. So it's going to be the convolution of this 1, because this is constant. It's undecaying. By the identical reasoning. And so what's the answer going to be? It's going to be the integral from 0 to t of f of u du. Now, that's an 1801 problem. If I dump with a dumping rate f of u, and I dump from time 0 to time t, how much is on the pile? They don't give it. They always give velocity problems and problems of how to slice up bread loaves and stuff like that. But this is a real-life problem. If that's the dumping rate, and you dump for t days, from 0 to time t, how much do you have left at the end? Answer, the integral of f of u du from 0 to t. I'll give you another example. Suppose I wanted a function, wanted to interpret something which grows, like t, for instance. All I want is a physical interpretation. Well, I have to think of, I'm making a pile of something, a metaphorical pile. We don't actually have to make a physical pile. And the thing should be growing like t. Well, what grows like t? Not bacteria, they grow exponentially. Before the lecture, I was trying to think of something, so I came up with chickens. I'm sure on a chicken farm, little baby chickens grow linearly. All little animals. Anyway, I've observed that babies grow linearly, at least for a while, thank God. After a while, they taper off. But at the beginning, they eat every 4 hours or whatever, and they eat the same amount pretty much, and that adds up. So let's suppose this represents the linear growth of chickens, baby chicks. Baby chick, that makes them sound cuter. Less offensive. Okay, so a chicken farmer, or whatever they call them, is starting a new brood. So anyway, the hens lay at a certain rate, and each of those are incubated, and after a while, a couple of months, they turn into little baby chicks come out. So this will be the production rate for new chickens. Okay? And it will be the convolution, which will tell you at time t the number of kilograms. We better do this in kilograms, I'm afraid. Now, that's not as heartless as it seems. The number of kilograms of chickens at time t. It really isn't heartless because, after all, why would the farmer want to know that? Well, because a certain number of pounds of chicken eat a certain number of pounds of chicken feed, and that's how much he has to dump, must have to give them every day. That's how he calculates his expenses. So he will have to know what the convolution is, or better yet, he will hire you who knows what the convolution is, and you'll be able to tell him. Okay, why don't we stop there and go to recitation tomorrow, because they'll be doing important things.